So before we move on to new material, I actually wanted to spend a little bit more time talking about monitors from last time, because I thought that our discussion was a little bit confused, maybe. So first, let's just review, the three main synchronization constructs we're talking about. Right. So the most basic one is we have a lock where you either acquire and release. Right, so that was the first thing we started with, and then we moved to a semaphore. And what were the two operations of a semaphore? Anyone remember? So first, yeah, right. So we have wait and signal. So remember what a semaphore is. So with a lock, it's just one thread either holds the lock or the lock is free. And so with a semaphore, remember that we're generalizing the idea of a lock. So you can think of a semaphore as maybe a pool of permits, right? So in a lock, there's sort of one permit, and you give that to one thread, and then no other threads can take the lock. But with a semaphore, this is basically an integer. So we could have a semaphore with a value of 3. In which case, the semaphore has 3 permits. And so whenever you call wait, a thread that calls wait is essentially taking one of those permits. So you're decrementing the value of the semaphore. So 3 would go to 2 is when something calls wait. And if the value of the semaphore is 0 or less than 0 and you call wait, then what happens to the value of the semaphore? So you're decrementing it, so what does its value go to? Well, no, so I said if it's, say we call wait a few times and it's now 0. So the next time we call wait, the value of the semaphore is going to go negative, right? And so when it goes negative, that's when we actually block the thread, right? So in the case of lock, when you acquire a lock that's being held by something else, your thread blocks. With a semaphore, you have some number of permits, and whenever you call wait, you're decrementing. And once you get to 0 and something calls wait, the value of the semaphore goes to -1 and the thread blocks, right? Because that basically means the semaphore has no additional permits right now, so you're going to block until a permit is available. And so similarly, when a thread calls signal, you're incrementing the semaphore, and if other threads are blocked on it, then you're going to wake up one of those threads, and it will, you're essentially handing off your permit to some other thread. Right, so that's the basic idea of the semaphore. Make sense? Yeah.
Is it locked on 0?
So the implementation we talked about last time was basically that when you call wait, you first decrement the counter, and then if the counter is less than 0, you block. Right? So remember, we can very easily implement a lock using a semaphore. And how do we do that? This is what we call a binary semaphore. So remember, when you create a semaphore, you have to give it, some initial number of permits, basically. So if you want to just create a lock, how many permits do you want to give it? Yeah, right, just 1. So if you create a semaphore with 1 permit, then the first thread that calls wait, it's going to decrement to 0 and keep going. And any other thread that comes in and calls wait, it'll decrement to -1 or potentially further than that, and will block. So only 1 thread at any time will be, holding the permit. Make sense? So, there were sort of 3 ways we talked about using semaphores. So one was just using it as a lock. So this was the idea of a binary semaphore. You set the value to 1 initially, and then it just works like a lock. What was one of the other things we talked about? Yeah. Right. So that's basically the idea of the pool of permits. So that's what we call a counting semaphore, where you have more than 1 permit to give out, and the value of the semaphore is going up and down. Anyone remember and then actually the third thing we talked about was we can do scheduling constraints using a semaphore, right? So for example, let's say we don't set the value of the semaphore to either 1 or greater than 1. Let's say we set it to 0. So if we have the initial value of the semaphore be 0, then what happens when the first thread calls wait? So if the value of the semaphore is 0, then how many permits are there to give out, basically? None. So if something calls wait, what's it going to do? Right, it's going to block even if it's the first thing calling wait. So we talked about last class how you could use that to basically impose an ordering between two events. So if you have, thread A, say we have thread A and we have thread B, and they're each, performing, some method, we have, method A and method B, and we want to say enforce that method A always runs before method B, we can use a semaphore with an initial value of 0, and then how can we use that to ensure that method A always goes before method B? Yeah.
Have method A signal to method B?
Right. So we have this semaphore. Let's just call it sem equals semaphore initial value 0, and method A we always want to run first. So we're going to have we can run this and then call, or rather, we can call semaphore dot signal, and in method B we can have semaphore dot wait. Right. So now if method B executes first, this is going to block because the value of the semaphore is 0, and then afterwards method A will come in. Oh, sorry, this should not be first. We want to have signal after this. Right, so if method B comes first, if thread B is running first, it's going to hit wait, and because the value of the semaphore is 0, it's going to block. And then later, thread A runs, executes method A, which we wanted to run first, so that's good, and then calls signal, which increments the semaphore, and so then what's going to happen once the semaphore has been incremented? Right. This is incremented the semaphore, so now thread B is done waiting and now executes method B. And if the scheduler ran thread A first, then that's fine. We call this, we signal the semaphore. Now the value of the semaphore is what? Right. It was initially 0. So if we're running this first, we still increment it to 1. And now we come in here, we call semaphore.wait, and the value of the semaphore is 1, so the thread doesn't block. The thread continues and does method B, which is fine, right, because method A has already run. So this is an example, yeah. Yes, yeah, so sem is just a specific variable that's a semaphore we're using. Right, so this is how we can use semaphores to impose these scheduling constraints where we want something to run before something else. Any questions on that? Make sense? Okay. So we talked a little bit about this last time, but now we're going to use a third type called a monitor. So basically, what are some of the problems with semaphores we talked about? Well, semaphore is sort of like this global integer that threads are calling and incrementing and modifying and blocking on, but we talked about how there are several different ways we could use semaphores. So often when you're actually looking at code that's using these things, it's not exactly clear, how the semaphore is protecting things or when things are blocking and whatnot. So essentially, semaphores are often a little bit complicated to actually use correctly. So we're going to introduce sort of an often nicer to use construct called a monitor. So basically, a monitor is a class, right? So we all know what classes are. So we have some class and we have some data. We have some basically shared data in the class. And then we have methods that operate on the data. So this is what we all know of as a class. It's some data and some methods for operating on that data. So when we're talking about a monitor, we're taking the idea of a regular class and we're augmenting it. First, we're going to introduce a lock. So there's going to be a lock as part of this monitor. And the lock's going to be used to enforce mutual exclusion among all of the methods. So whenever you enter a method of a monitor, you're going to acquire the lock, and whenever you leave a method of the monitor, you're going to release the lock. Right? So the effect of that is that you have a bunch of methods, and you're guaranteed that only one thread is executing inside the monitor at once, right? So this lock is giving you mutual exclusion for all of your methods. And then the other thing that we're going to add is, well, actually, let's first just look at a very simple example of this. So here we have an example of using monitors in Java. So Java actually makes it really, really easy to do monitors. This is basically the producer-consumer problem again that we've talked about a few times, where we have some queue of data, and some threads are coming in and calling add to put things onto the shared queue, and some threads are coming and calling remove to take things out of the queue. Right? Standard problem we've talked about a few times. So in Java, when you want to make something a monitor, right, we want these add and remove to have mutual exclusion because we don't want two things to be adding at the same time, or add and remove to be happening at the same time, because they're both operating on that shared queue data structure. So all you have to do is you have to add the synchronized keyword. So when we're saying these methods are synchronized, Java is actually using a lock. And you see that we're not having to call anything on the lock. Java is essentially doing that for you. We're just saying we want these methods to be, to have mutual exclusion, and Java itself, whenever some thread calls add or remove, it's going to acquire that lock, and then once the thread exits, it's going to remove the lock. Right? So pretty simple. All we're having to do is add one word to each method, and we're getting mutual exclusion on all of our methods. Questions on that so far? Okay. So, one piece that's missing from this, as it's written up here, is, so when we want to add something, we take control of the lock, we add the item to the queue. When we want to remove something, if the queue isn't empty, well, of course, first we take control of the lock, which we don't have to write. And then if the queue isn't empty, we remove the item and return it. So what's missing here is what happens if the queue is empty. So suppose what we want to do is, if the queue is empty, we want to wait until something's been added to the queue. So essentially what we want to do is we want the thread to wait until add has been called and something's been added to the queue. So what's the problem there? Yeah.
If you're waiting for something to be added, it's currently locked on the date.
Right, great. So remember, these, we have this monitor lock in here. And whenever a thread is executing in one of these methods, you're holding the lock. So if you're in remove and you essentially want to go to sleep, you're still holding the lock. So if you go to sleep here, waiting for someone to call add, is that ever going to happen? I mean, someone might call add, but anything that calls add is going to block because you're still holding that lock. Right, so that's essentially the problem here, is that while you're holding the monitor lock, you might want to be able to wait on certain conditions, like an object being added. So to deal with that, we're going to introduce this idea of condition variables, which are the other main part of the monitor. So remember, the two things we're adding to, the basic idea of a class are the lock, the one monitor lock, which is always there, and then this idea of condition variables. So the idea here is that using a condition variable, you can essentially wait for a condition to happen and simultaneously release the lock. So that's that's basically going to enable us to solve the previous issue where you're still inside the critical section, but you're going to sleep and releasing the lock. And then once you wake back up, once the condition has changed, then you're going to reacquire the lock before continuing to execute. So basically what a condition variable is it's a queue of threads that are waiting for something to happen inside that critical section. So remember, whenever they're in the monitor method, they have the lock, and then when they wait on a condition variable, they're giving up the lock until that condition has changed. So condition variables themselves basically have three operations. We have wait, signal, and broadcast. So remember, this is so remember, for condition variables, we have the wait and signal and broadcast. So remember, just to keep things straight, Semaphore has wait and signal. Condition variables also have wait and signal, but they're going to operate a little bit differently, and we'll talk in a minute about how that is. But so basically the idea is when you call wait, you're holding the lock, because you're inside the monitor method, you're giving up that lock and going to sleep while waiting for that condition to change. And then sometime later, when the condition has changed, when a thread has added something to the queue, for example, that thread is going to call signal, and you're going to wake up the thread that was calling wait. So that thread was previously blocked and waiting. Once something calls signal, you wake it up. And broadcast is the exact same idea, except you're waking up every thread that is waiting on the condition, right? Because remember, a condition variable is basically a queue of threads that are all waiting on the condition. So signal is waking up one thread, broadcast is waking them all up. That's basically the only difference. So let's look at how we do this in Java. So just a notation thing, in Java, the methods are not called wait and signal, but wait and notify, but it's the same idea. Wait and signal is how we generally talk about these things. But so here we have the same thing as before, where we have these two synchronized methods. And so we just added two little things here, basically. So when we're calling remove, we're going to say while the queue is empty, and we're calling wait. So when we call wait, the thread that's in here has the monitor lock. It's going to give up the lock and go to sleep. That's what's happening when we call wait. And then sometime later, some thread is going to come in, put an item on the queue, and call notify. And so once we call notify, the thread that was previously waiting is going to wake up and actually have an item that it can remove and return. Any questions on this so far? Yeah.
In multiple conditions, we have to have multiple waits and multiple notifies.
So is your question basically about using multiple condition variables?
Yeah, we have different conditions.
Yes. So essentially, when we're calling wait and notify here, we're calling them on a specific condition variable, which is not explicitly defined. I mean, the way we're using it in here, right? The condition is basically the queue is empty. Like that's what the condition is, even though we haven't sort of explicitly said what the condition variable is. In Java, these, wait and notify here, we notice we're not calling them, we haven't said what object we're calling them on. So these are actually saying, this is the same as saying this.notify and this.wait. It's calling it on the current object. So in Java, this is just specific to Java, we're using this class, because remember, a monitor is basically a class. We're using this whole class as a monitor, and in Java, each monitor basically has one condition variable associated with it. So if you wanted to have other condition variables, you'd have to have other objects, and then you could call wait and notify on those other objects. In this case, we're just using the one condition variable and calling it on the current class. Does that answer your question?
Yeah.
Okay. Other questions so far? Yeah. You're asking if you call. Are you asking if you call notify what thread gets woken up? Is that what you're asking? Right, because if you have multiple threads come in here and all call wait, then you have multiple threads waiting on the condition. In this case, we're calling notify rather than notify all, so we're waking up one thread. In general, the exact thread that's woken up is basically implementation specific. I believe that Java essentially makes no guarantee about which thread gets woken up. Right, well, think about what happens. If we have, say, 5 threads that all call remove, so we now have 5 threads waiting, then, subsequently, as threads come in and call add, we're waking the threads up one at a time, and each thread that gets woken up is going to take the item that was just added. Does that make sense? Okay. Other questions? All right, so there's one little thing here that I haven't talked about, and that's this while loop. So anyone have any idea why we have a while loop there? So I basically didn't say exactly what happens when we call notify, right? Because remember, when we call notify, this thread that's calling notify still has the lock. And notify doesn't put the thread to sleep. When we call wait, we put the thread to sleep. But when we call notify, I essentially didn't say exactly what happens. So we essentially have two different types of monitors. We have Mesa and Hoare monitors. And the difference is what happens when you call signal, or remember it's notify in Java, but essentially it's the signal operation. And so in Mesa-style monitors, when you're calling signal, the thread that is holding the lock, which is the thread that's calling signal, continues to hold the lock. And so the thread that you just woke up, so remember, when we called notify, we just woke up this thread. This thread is still in the critical section. So it needs to reacquire the monitor lock before it can actually keep executing. Right? Because this was the whole point, is that we want to be able to wait inside the critical section. So we need to have the monitor lock before we can proceed. So in Mesa-style monitors, which is what Java uses, the thread that calls notify still has the lock. And so it's going to keep executing. And once it exits the method, we have, this thread here wants to acquire the lock. But there might be other threads that also want to acquire the lock, right? Because there could be other threads that are, trying to call, say, remove. So does anyone see why that means we actually need this while loop? So if we didn't we called notify, but we didn't actually give the lock to this thread. So what might happen before this lock actually gets control of the lock again? Before this thread gets control of the lock again? What could happen? What? The queue is not empty. Well, we know the queue is empty right after this thread has the lock, put an item on the queue and called notify, and then exited the method and released the lock. At that point, we know that there's an item on the queue. But what could happen now? Remember, we woke this thread up, but it doesn't have the lock yet. So what could happen? Yeah.
It could be empty again.
Because why? Why could the queue be empty again?
Because the thread before it could have removed.
Right, exactly. So, we released the lock here, but this thread doesn't have the lock yet. So another thread could come in and basically take the lock first, take the item and remove it. And now the first thread that was originally waiting subsequently gets the lock and finds that the queue is actually still empty, because some other thread essentially beat it into the lock and took the item before it could. People seeing how that works? So you need this while loop because you don't actually know that the queue won't be empty again between the point where you woke up and you got the lock again. Some other thread could have come in and take the item before you. So that's the idea. That's what Mesa-style is, where the thread that signals keeps the lock. The second style, the Hoare-style monitors, what we're doing is when we call signal, we immediately give the lock to the thread that we're waking up. So what happens here then is we call notify, and we immediately hand the lock to this thread. So if we're doing that, do we need this while loop here? Right, we don't need the while loop there because we know that this thread now has the lock, so no other thread can come and grab the item. So if we're using Hoare-style monitors, this can be a regular if statement, which in some sense makes more sense. The only difference between the two types is that when we're using Mesa, we need to repeatedly check the condition because of the fact that you're not given the lock immediately. Make sense? Yeah.
So why do they use Mesa?
You mean why do, most real operating systems use it. I don't actually know offhand if there was a specific reason for that. It may just be convention that since most OSs have done that before, they continue to. Again, the differences are fairly minor. In most cases, when you're programming real code and you're using Mesa-style, the only thing you have to remember is you need to do the while loops where you might think that an if statement makes more sense. That's essentially the only difference. So, yeah, so this is basically what I just said. If we're using Hoare-style monitors, exactly the same thing, except we can change that while to an if. So, I talked about monitors in Java, so now let's look at monitors in C++. Here it's going to be a little bit more complicated because Java is really nice with that synchronization keyword that is basically handling all of the details of the monitor lock for you. You don't have to even be aware that the lock is there. C++ doesn't have that, so you actually have to manage it yourself. So this is essentially the same program in C++. And so the main difference here is where we don't have a synchronized keyword, so we have to manage the lock ourselves. So we have this lock variable, and we have our two methods that we want to have mutual exclusion. So we are just locking at the beginning of the method and unlocking at the end of the method. So that is essentially what the synchronized keyword is doing in Java. We're just doing it manually here when we're locking and unlocking. Now note that this does give you the flexibility to, for example, lock for only a subset of the method. Because in Java, when you say the method is synchronized, the entire method is surrounded by the lock, the acquire and release. Whereas in C++, we're essentially defining where we want the acquire and release to be. But then everything else here is essentially what we already said. We have a condition variable, which again was sort of implicit in Java. We were calling this.notify and this.wait. In C++, we're doing it more explicitly. We have condition var, and we're calling wait and signal on that. And when you're calling wait, we have to pass the lock explicitly because again, C++ isn't managing that automatically for us. But essentially, this is the same program, just using the C++ where we're doing a little bit more manual management. Questions before I move on? Okay. So let's look at the bounded buffer problem using condition variables. You may recall from last time we looked at this problem, how to solve it using semaphores, and we had this solution that was kind of complex and unintuitive that involved 3 different semaphores and a lot of waiting and signaling, and it was just kind of a mess to read. So this program is going to basically make more sense when we're using condition variables. So remember, this is again the same program where we have a shared buffer of items, and you're calling append and remove. And what are the 2 scheduling constraints we talked about here? So we have threads calling append and we have threads calling remove. And what are the two constraints that say when append and remove can run? Yeah. Right. Yeah. So if the queue is empty, if there are no items, then clearly we can't remove an item. So that's one constraint. And if the buffer is full, has no available empty slots, then clearly we can't append anything to it. So we can very easily just express those 2 conditions using 2 condition variables, full and empty. So it's pretty straightforward here. We again are here doing the locking and unlocking ourselves. But we're basically just saying when we're calling append, if count is n, which means that the buffer is full, there's no space to add something new, we're going to call wait on empty, and then subsequently when we remove something, we're calling empty.signal, right? Because we know that there's now at least one empty space if we've just removed something. So we're calling signal and empty and waking up the thread that's in append. And similarly, we're just doing the reverse for remove. When we call remove, if there's nothing in the buffer, we have to wait. So we're calling wait on full. And then once something is appended, we're calling signal on full, and that's going to wake it up again. Right? So this is kind of more intuitive because we're explicitly saying, I want to wait until this condition is true, as opposed to earlier where we had sort of a whole bunch of semaphores and we're just calling wait and signal all over the place, but it's sort of not, it's not as clean as using condition variables as we're doing here. And again, this is using Hoare-style monitors because we just have an if here. If we were using Mesa-style monitors, exactly the same, except both of these if statements would need to be whiles for the reasons we talked about a moment ago. Questions on this? Okay. So now let's briefly just consider the differences between semaphores and monitors. So remember, semaphores have wait and signal. And condition variables also have wait and signal. So of course, the natural question to ask is, well, are condition variables and semaphores, basically doing the same thing? So what do people think? Are they basically the same thing? So let's first construct a little example. So let's say we have thread A, and thread B. And let's say that thread A is calling wait, and thread A is calling signal. So first, let's say that they're calling these on semaphores. Let's say S equals semaphore with initial value say 0. So let's say that thread A runs first, and we're using semaphores. So what's going to happen when we call s dot wait? What's going to happen to thread A? Yeah, right. It's going to block. The value of the semaphore is 0. It's going to go down to -1, which is less than 0. So thread A blocks. Now later we call thread B, which calls s dot signal. So now what's going to happen? Yeah. Right. It bumps it back up to 0, but it also is going to wake this thread up because there's one waiting. So we call signal, thread A wakes up and continues running. So now let's say that we're using condition variables instead of semaphores. So what's going to happen now? So now we're in thread A and we're using a condition variable and we call wait. So what's going to happen? So what does wait do in a condition variable? Remember, it does two things. What are the two things it does? Yeah. Right, it releases the lock. That's the first thing. And what's the second thing it does? Right, it releases the lock and puts the thread to sleep. So thread A is going to go to sleep, release the lock and go to sleep. Now sometime later, thread B calls signal. This is again condition variable, so what's going to happen? Yeah. Well, remember, with condition variables, thread B has to hold the lock in order to call signal. But what's going to happen to thread A once thread B calls signal? Right, so thread A is going to wake up again and keep executing. Right, so basically in this case, essentially the same thing happened with condition variables and semaphores. Right, the first thread blocks, and then the second thread came and called signal and woke up the first thread. Right, so that was essentially the same behavior with the semaphore and the condition variable. But now let's say that thread B executes first. So let's suppose we're using semaphores. So semaphore with initial value of 0. Thread B comes and calls s.signal. So what's going to happen to the value of the semaphore? Yeah. Right. So the value of the semaphore is going to go from 0 to 1. And now sometime later, thread A calls wait. And what's going to happen? Yeah. Right, the value goes back to 0, but the thread doesn't block, right? Because we called signal, we incremented the value of the semaphore up to 1, so now there's a permit available. And so then when we call wait here, thread A takes that permit and keeps executing. So that was with semaphores. Now if we're doing this with condition variables, we call signal here, and what happens? If thread B is running first again, this is the scenario. So thread B calls signal on a condition variable, and what happens? Yeah. Right, nothing happens. Nothing's waiting on the condition. There's no number to increment. That's essentially a no-op. Nothing happens. So now sometime later, thread A calls wait, and what happens? Right, thread A does what we said wait in a condition variable does. It gives up the lock and goes to sleep. Right, so this is not the same as what happened in the semaphore case. In the semaphore case, this thread, when it called wait, decremented the semaphore but didn't block. Whereas in the condition variable case, when you call wait, you're always blocking. So clearly this is showing that there is some difference between how semaphores and condition variables are working. And so essentially what's going on here is that semaphores have some kind of memory, basically, of the waits and signals that were previously called. Right? Semaphores are basically a number that's getting incremented and decremented. And so calling signal in advance of this wait is essentially giving the semaphore memory that signal was actually called, and so the next thing that calls wait is not going to block. Whereas condition variables essentially have no memory. When you call signal, if nothing is currently waiting, nothing happens. And when you call wait, you're always going to sleep. And it's only with a subsequent signal that you might actually get woken up. Make sense? So, condition variables essentially don't have state. Semaphores are maintaining the state in the form of that number that's incrementing and decrementing. So that's one major difference. Here's actually another good question. So when we're considering a certain order of calling wait and signal, let's say we have a bunch of threads that are all calling wait and signal, and they could be interleaved in sort of any order. So does the order of execution with a semaphore matter? Yes. Does it? So what's happening to the value of the semaphore every time you're calling wait? Right, and every time you call signal, right, so if you're adding 1 a bunch of times and subtracting 1 a bunch of times, does it matter sort of the order you do those? I mean, it may matter while the things are executing, but like at the end of it all, right, the semaphore value is always going to be the same. You're incrementing and decrementing, but ultimately, you're going to have the same result. Whereas that's not true with condition variables, because as we said, signal is doing nothing if nothing is waiting. So the order of execution is actually very important there. So we can summarize that as saying that semaphores are commutative, where the order of execution doesn't really matter. Condition variables are not commutative. The order of execution does matter. And then one final thing is that, remember, we define condition variables that have to work in the context of that monitor lock, right? Because they're very tightly linked to a monitor. They're giving up the lock before they go to sleep. But what happens if you try to use a semaphore inside a lock? What might happen? Yeah. Right, so you get a deadlock, and why might that happen? Fair enough. Anyone have any idea? So if you're in a lock, if you've acquired a lock, and you now call wait on the semaphore, and let's say the value of the semaphore is 0, the thread goes to sleep, but you still have the lock. Remember, this was essentially the problem we were trying to avoid by introducing the idea of condition variables, which is, in general, you don't want to have a thread holding a lock that goes to sleep, because if it's waiting on some other thread to take the lock in order to wake it up, that's never going to be able to happen. So that's why you can get a deadlock using a semaphore inside a lock. Whereas by definition, you're always using a condition variable inside a lock, because that's how we designed it to work. Questions on that? Okay. So this is essentially what we just covered. And I don't want to go into details, but essentially you can implement monitors using semaphores. And essentially the key point is just enforcing those differences we just talked about. So, when you call wait in a semaphore, you don't necessarily go to sleep if you just call wait on a semaphore. So we have to add some additional logic to ensure that you actually always do go to sleep. And then in signal, we only want to increment the semaphore that we're using if someone's actually waiting. So again, I won't go through all these steps, but basically when we're calling signal on the condition, we only want to increment the semaphore if something is actually waiting. And if nothing's waiting, then calling signal does nothing. Remember, because that was one of the key differences between semaphores and condition variables. Okay, so any last questions on semaphores and monitors before we move on? Okay. So now we've basically talked about our 3 basic constructs for doing synchronization. We have locks, semaphores, and monitors. And so now, and then we looked at the producer-consumer problem from a few perspectives. So now let's look at some other types of problems where we're essentially looking at a shared data structure that multiple threads are accessing, right? Because that's essentially the fundamental problem we're trying to solve in all of this. So we're going to look at 2 other synchronization problems, the reader-writer problem and dining philosophers. So first, let's talk about the reader-writer problems. So the idea of the reader-writer problem is you have some shared piece of data. It doesn't really matter what the data is. It could be an array. It could be an object. It could essentially be anything. And you have multiple threads that are either reading or writing the data. So what's sort of the trivial approach to ensure that you're doing that safely? To ensure that multiple threads that want to read and write the data can do it safely? What's sort of the most trivial thing you could do to solve that using one of our synchronization constructs? Yeah. Even simpler. What's the simplest possible thing? What's our most basic synchronization construct? A lock, right? So all you really have to do to solve this problem is if someone wants to read or write, you take the lock, and then you do your read and write, and then you release the lock, right? And you've essentially solved the problem. No one is going to be reading or writing concurrently, so it's safe. But so what's the problem there? Why is that not ideal? Yeah.
You're limiting the scalability because if you have 100 readers and one writer, then even though the 100 readers are modifying the object, they still have to apply the lock.
Right. So the idea here is that is essentially meaning you cannot have any parallelism. You're only having one thread either reading or writing at the same time, whereas in practice, it's okay for multiple things to be reading an object at the same time. It may not be okay for multiple things to be writing at the same time, but if you have an object that's not changing, you can have 100 different threads reading it as long as they're not changing it, and that is fine. And so that is, giving your program concurrency and parallelism that you can't have if you're just having one global lock. Right? So the way we're framing this problem is that we have a bunch of threads, and each thread is either doing reading, it's a reader thread, or it's writing, it's a writer thread. And so what we want to allow is we want to allow for multiple readers to run at the same time. They can all read the data structure at the same time. We only want to allow one writer, of course, because if you have multiple things writing at the same time, they can overwrite each other. So we don't want that. And what about a writer and readers at the same time? Is that okay or not okay? What do people think? So if you have some things reading at the same time and someone else is trying to write while you're reading, is that yeah? What? It'd be a bad idea. Yeah, in general, that's not going to be safe, right? Because if you are changing and say it takes a while to do the writing, you could essentially take your data structure and leave it in an inconsistent state while things are still reading. Now, of course, if you can update your data structure atomically, if you can do that basically in one step, then maybe that's fine. But in general, we're going to say that that's not safe. If you have something writing, you don't want anything to be able to read at the same time. So that's the reader-writer problem. Any questions on sort of what the problem is? Okay. So let's look at how to solve this using semaphores. So we're going to use essentially two semaphores to do this. We're going to have some integer that's counting the number of readers. Initially, there's going to be no readers. And we're going to set the initial values of the mutex and the write semaphore to 1. So let's look at how this works. So first, let's look at the write. So the write is really, really simple. So we have this, this write semaphore that we're going to signal. And remember that write semaphore had an initial value of 1. So when we signal it, the first thread that calls wait, or sorry, not signal, but the first thread that calls wait is going to decrement the value of the write semaphore to 0 and continue executing and start performing the write. So now if another thread comes and tries to call write, what's going to happen? Right, it's going to block because while the first thread is performing the write, the value of the write semaphore is 1. It was 1 initially, so what is it while the first thread is doing the write? 0, right? So if another thread calls write, it's going to go to -1, and that's going to block the thread. And then once the first thread is finished, it's going to signal on the semaphore, which will increment it back up to 0, and the previous thread that was waiting will start executing again. So write is pretty simple. It's essentially it's just using a global lock to ensure that there's only one writer at a time. So now let's look at the reader case. So in the reader case, we're first going to take control of this mutex lock. We're going to call wait on that. And then we're going to increment the number of readers, right? Because another reader has arrived. Now, if this is the first reader, then we're going to call wait on the right semaphore. Right? And so that's going to effectively have the effect of blocking writers from entering. Right? Because that's how we're using it here. Whenever we're calling wait on the right semaphore, it's ensuring that no other writers can arrive. So we were talking about calling it in the write method, but we could also call that in the read method. So once a reader arrives, we're calling wait on the right semaphore, and so if a writer subsequently arrives, it's going to block. It's not going to be able to enter. Even though there isn't an existing writer, we just called wait from the earlier reader. So then, the reader is going to perform the read, and then, take this mutex lock again, subtract 1 from the count of the currently active readers, and then if readers is 0, then what does that mean? If we're a reader here and we get down here and the value of readers is 0, what does that mean? Yeah. Right. If the value of readers is 0 down here, it means I'm the last reader and I'm exiting. I've finished my read, which means it's now safe for a writer to go. Right? Because there are no other outstanding readers if the value of readers is 0 down here. So we're going to signal the right semaphore. And if we have a writer up here waiting on that, it's now going to be allowed to run. So one thing I didn't talk too much about is this other semaphore, this mutex that we're calling wait and signal here, wait and signal here. So first of all, is that we're basically using that just as a regular lock. That's another binary semaphore we're just using as a lock. So is that locking the point where we actually do the read? No, right? Because the whole point is we want concurrency in the read. We want multiple readers to be able to read at the same time. So we're explicitly not locking around this part where we're actually doing the read. But we are locking about these other points. Why are we doing that? Yeah. You only want one person to tell the writer to wait. And why is it that you might tell multiple people, why might you have multiple threads that tell the writer to wait? Right, so basically the idea is readers is another shared data structure. Or not, it's just an integer, but readers, that integer is another piece of shared data that multiple reader threads are working with. So we're essentially just using this lock to protect the value of readers, to ensure that we are, only one thread is changing readers at a time, and then only one thread is performing this check at once. So mutex is essentially just being used as a lock to protect the readers variable. So we already essentially talked about, how a reader blocks a writer. We have, the first reader that comes in calls wait on the right semaphore, and that blocks writers from executing. How does a writer block a reader from? How does a writer block a reader from executing? Yeah.
If reader is equal to 1, then waiting on WRT will put that thing to sleep.
Right. Because if we have a writer in here, then what's the value of the right semaphore if we have someone currently writing? Right. The value of the right semaphore is 0 if we have someone currently writing. So then when we have a reader arrive, it's going to take this lock, that's fine, right? The writer is not using this mutex lock. It'll increment readers, and if it's the first reader, then it's going to hit write.wait, and that's going to block, right? Because someone is currently writing, so if a reader calls write.wait, that's going to block. Right, so that will account for the first reader to come in. The first reader that arrives is going to block. What happens when another reader arrives? Yeah.
It's going to wait because
Right, because remember, after the first reader arrived, readers is no longer equal to 1. Or rather, if we have a second reader that's down here, it would increment readers to 2 and wouldn't actually execute writer.wait. So it's not going to block for the same reason it's a first reader. But this first reader, which is now blocked here, is holding the mutex lock. So any subsequent reader that arrives is going to hit mutex.wait and is going to block there. So subsequent readers are only going to be allowed to execute once the first reader releases the mutex lock. And when is that going to happen? Yeah. Right. That lock is only going to be released once the writer actually finishes and releases the lock. And once the writer is done, it's fine for readers to start executing again. So the first reader is going to stop being blocked here, release the lock, and start performing the read. And once this lock is released, all the other readers that are queued up will start executing this. They'll execute this little block of code and start performing the read, and the next one, and the next one, and so on and so forth. Then you essentially have all of the readers start doing their reads. Make sense? Questions on that? So this is essentially enforcing one writer at a time. You can have multiple readers, but you can't have readers if there is currently a writer. Yeah. Is it possible for the writer to never be able to write? Great question. So, this is a correct solution. This ensures the behavior of the reader-writers as we want it to. But is this a good solution? So one way of saying it was a good solution is the solution fair? So what do you think? Right. As long as there's a reader here, the writer is never actually going to be able to execute. So once you have the first reader come in and block the writers are now blocked. But is anything preventing additional readers from arriving? Right? Readers can continue to arrive, and subsequent readers are never even calling writer.wait, so they're essentially not waiting on any writers that might be waiting. So you could have readers continuously arrive and essentially lead to starvation of the writers. Right? This solution is explicitly favoring readers over writers. So writers that are queued up are going to have to keep waiting until all the readers are actually done, even if the writers have been waiting much longer than readers. Because there's nothing that enforces that readers have to actually wait until after a previously arrived writer. Make sense? Questions on that? So we already talked about these scenarios. So we can actually look at a different solution where this is also actually not going to be really fair, but we can essentially consider the opposite approach of favoring writers rather than readers. So the idea here is going to be basically the same thing. I won't go into all the details of this, but basically, once the first writer arrives, we're going to block the reader. And then it's going to be the same thing as before in reverse, where we're maintaining a counter of the number of writers, and once all the writers are finished, then we're calling signal on a semaphore that's going to allow the readers to start running. So this is essentially the opposite approach, where once the first writer arrives, readers are blocked and are going to keep queuing up, even as writers continue to arrive and essentially skip the queue and get to execute one after another. And it's only after writers are completely finished that readers will be able to actually run. Yeah.
Wouldn't the solution be preferable if writing was rare?
If writing was rare.
If you rarely had a writer, you really wanted that writer to get
Yeah, so you could certainly consider scenarios in which maybe one or the other of these might be useful. So here's a simple contrived example. Let's consider you had a stock ticker application where the values of stocks were changing, and you had a lot of threads watching stock values, and occasionally the value of the stock updates. And so probably that's the kind of thing where you would rather update it immediately and have readers get the correct value a little bit later as opposed to getting an incorrect value now. So that might be a type of application where you actually do want to favor writers and get the writers in immediately. And if there are few writers, then chances are you're not going to, that's not going to lead to starvation, most likely. But, I mean, you could construct a scenario in which you might want to prefer writers or readers. But what might a fair solution look like, right? Like, these solutions are essentially explicitly not fair. So what would a fair solution look like? Yeah. But just sort of intuitively, what would sort of be the fair approach? Like, what's the objective, right? Because here, if you have writers, they keep running. So you're saying essentially balance readers and writers. So maybe that's true if you have, say, an equal number of readers and writers. But what if you have a ton of readers and only a few writers? Right, so you could try to keep like an even level of weighting readers and weighting writers. Is that what you're saying? You could do that, but again, if sort of the rates of arrival are different, that still might not be exactly fair. So what might a different fair approach be? Yeah. Right, so essentially, returning to our favorite simplistic scheduling algorithm, we can essentially do something like, first come, first serve, where, we have, a queue of requests, and each request is either a read or a write. So maybe, this is the most recent request. And so, maybe this is the request that's been, waiting the longest. So this will be the next one to run. So maybe we have, a read, then another read, then a write, and then, 3 more reads, and then, a write, so on and so forth. And, the fair thing to do would be basically to, run them in order. And so, the way that would look is you essentially take off all the readers at once. So if we're here, we can now run both of these readers at once. They're going to execute concurrently. But then we're not going to accept any more readers until this writer has been given a chance, because it was next in line. So we'll run both of those reads, and then run this write by itself. Once that's done, we can take the next cluster of reads and run all of these simultaneously, and then wait for the next writer, and so on and so forth. People see how that's working? So you're still getting concurrency, because you're taking multiple readers at a time and running them, but you're ensuring that you're not actually getting starvation. So I'm not going to show any code about how to do this, but intuitively, this is a pretty straightforward idea. You're just going to run it in order and essentially take concurrency whenever you can, which is when you have multiple readers back to back. Questions on that? Okay. So let's get those. So let's look at how to do this in Java. So first, let's look at doing this using monitors, which is kind of simpler. So again, remember we are using the synchronized method. Synchronized methods are again where we have the implicit lock that's locking at the start of the method and unlocking at the end of the method. And so this is showing the read component. So when we want to call read, so first thing to note is this read method is not synchronized. And why do we want that method to not be synchronized? Yeah. Right, remember this was the whole point, is we don't want to have one global lock that's not allowing any concurrency. We want to be allowing multiple readers to run at once. So this method is explicitly not synchronized to allow multiple readers to run. So we're going to call, prepare to read, and while there is a writer, while there's at least one writer running, we're going to wait. So remember here we're again using a condition variable. And then, once the writers are all finished, we're going to increment the number of readers, do the reading, and then once you're done reading, decrement the number of readers, and if readers are 0, you're going to call notify, which, again, basically means that no readers or writers, either a reader or a writer, can now start executing. So this approach is also essentially favoring writers. right? Because while there's at least one writer, readers are always waiting here. So this approach is essentially the favoring writers approach. So this is the write component of that. So here, the write method is synchronized, right? Because we only want to allow one writer to execute at once. Multiple readers is fine, but only one writer. And similar idea here, we're first calling this prepare to write, incrementing the number of writers, waiting until readers are done. And so remember, once we've incremented the number of writers, then any readers that are arriving are immediately waiting. So that's why, again, we're favoring writers here. And then once all the readers are done, we can actually go and do the write, and then once we're done, we're calling num_writers minus and finally notify it. So one other thing to note here is that these methods, prepare to write and done writing, are not synchronized. But if we look previously, in the read case, these methods were synchronized. So why is that? Why is it synchronized in the read case but not in the write case? So synchronized here, not synchronized here. Yeah.
Because the method that calls those methods is synchronized.
Right. Because remember, these methods are only called from within this method. And this method is synchronized. So what that means is any thread that's executing in here already holds the lock. So even though these methods are not synchronized, is it ever possible for two threads to be in one of those methods at once? No, right? Because that's impossible, because anything that's calling them has to have already taken control of the lock. So we needed them to be synchronized in the read case because this read method, the main read method, was not synchronized. So we could have multiple methods calling prepare to read at once. And so because of that, we need to make prepare to read and done reading synchronized in the read case. Make sense? Questions on that? Okay. So, we've given a couple of examples about how to, do this read-write, approach. Now, the good news is that in most cases, when you're actually writing programs, you don't actually have to go and write this kind of code to manage readers and writers, yourself. Most programming libraries, such as Java or pthreads, basically provide out-of-the-box support for doing this using what's called a read-write lock. So a lock is sort of a very basic thing that languages give you, that you can just use a lock. You don't have to worry about sort of how to implement it internally. And similarly, a read-write lock is the same idea, except it gives us this reader-writer property of you can have multiple threads holding the read lock, but only one thread can hold the write lock. So if you're programming in Java, for example, you have this read-write lock class, and it has two methods, read lock and write lock, and they basically do exactly what we've described. You can have multiple threads call read lock, and they can all hold the read lock at once, and only one thread's going to be able to hold the write lock. And pthreads has a similar thing. Essentially, this is the same thing of we've talked sort of about how you can actually implement these useful low-level primitives, but in practice, most programming environments actually give you very nice, easy-to-use abstractions for doing this kind of thing. So that's it for the reader-writer problem. Now let's move on to the second problem, which is called dining philosophers. So the idea here is it's lunchtime in the philosophy department. So you have a bunch of philosophers sitting around a table eating lunch. And what do philosophers do around a table when they're eating? They're either thinking or they're eating. Those are the two operations. And so there's a chopstick in between each plate. So if you have five philosophers around the table, then there are 5 chopsticks. There are forks here, but it makes more sense if you consider them chopsticks. And of course, when you're thinking, you don't need to do anything. But when you're eating, you need 2 chopsticks in order to be able to eat. So when you want to eat, you need to pick up your left chopstick and your right chopstick, and then that will allow you to eat. And, of course, if your neighbor has already picked up one of those chopsticks, because remember, these are basically, each chopstick is shared between two philosophers. So if you try to pick up a chopstick that's already taken by one of your neighbors, you essentially can't do that. So you're going to block. And you're not allowed to, reach across the table to grab some other chopstick. You just have to use the one to your left and your right. So, the question here is essentially, how do we make sure that the philosophers can eat lunch without starving to death? So that's basically the problem, is we need to deal with the fact that we need to make sure that they can actually pick up the chopsticks and eat and not get stuck in a position where no one can eat and they all starve to death. Questions about how the problem is set up? So again, we could consider, what's again the trivial solution here? What's the obvious way that you can solve this? Yeah. Right. Just use another global lock and say that when you have the lock, you pick up your left chopstick and your right chopstick and you eat, and then you release the lock after you're done eating. And if you don't hold the lock, you're not allowed to pick up either your right or your left chopstick. So if you do that, then you're guaranteed that things will continue moving, the philosophers will get to eat, and no one will starve to death. But of course, that's very, very inefficient, particularly if you have a whole lot of philosophers. You, of course, want to allow multiple philosophers to eat at the same time. So we, of course, don't, we again want some concurrency here. We don't want just the trivial solution of using one global lock. So let's look at one approach to doing this using some semaphores. So we're going to have 5 different semaphores. We're going to have an array of semaphores here, each corresponding to one of the 5 chopsticks if you have 5 philosophers. And so the idea is when you have a philosopher that wants to eat, you're first going to wait on the chopstick to your left, and so then you'll wait on the chopstick to your right, and now you've picked up the chopsticks, you can actually eat, and then you're going to call signal to actually drop the chopsticks. Right? And so, of course, you're assuming that the values of the semaphores are 1 to begin with, so that if 2 people try to call wait on the same chopstick, the second one is going to block. Right? So pretty simple idea. You pick up one, you pick up the other. If one of them is either one of them is occupied, then you're going to block while trying to do that. So, what do people think? Does this work? Yeah. Right, exactly. The problem here is that you can lead to a situation where the philosophers all deadlock and starve to death. If each of them, say, picks up the left chopstick, then all the chopsticks are now taken, and no one's going to be able to pick up the right chopstick. So, the left chopsticks are now never going to be released, and the right chopsticks are never available, so everyone is deadlocked. So this solution doesn't work. So we have to do something a little bit, more intelligent than this. So basically the idea here is that before we actually go and pick up one of the chopsticks, we want to check if both of the chopsticks are actually available, right? Because the problem comes is if you pick up one chopstick but the other one was not available, then you're stuck. That's sort of the bad situation that we want to avoid. So if one of the chopsticks is not available, then you don't want to pick up anything until your neighbor's finished. So essentially, that's what we're doing here with this by adding this test method. So when you want to pick up a chopstick, well, so first what we're doing is we're taking the philosophers and they're all thinking initially. They're not trying to eat. And so when we want to pick up a chopstick, when philosopher I, say philosopher 3 wants to pick up a chopstick, philosopher 3 is now hungry, meaning they want to pick up the chopsticks. And so then we're going to call test I. And so what test I is basically doing is saying, is my left neighbor eating or my right neighbor eating? Because if either of those are true, I know that I'm not going to be able to pick up both my chopsticks and start eating. So if either of those are true, then, so if either my left neighbor or my right neighbor is currently eating, then I'm not going to set my current state to eating. right? Because if neither my left nor my right neighbor are eating, then I'm fine. I can pick up both and start eating. But if I can't do that, I'm not going to set my state to eating. And so then back here, my state will not be eating, and I'm going to call wait. So that's going to essentially block the thread. So the philosopher will not try to pick up the chopsticks right now because it's waiting on one of the neighbors. And then similarly, when you're calling put down, you are calling test for both your left and your right neighbors. And essentially what that's doing is it's saying if either my left neighbor or my right neighbor is waiting on one of the chopsticks I'm using, then call signal on them. That's what this is doing over here, calling signal on that neighbor, which is going to wake them up so that they can actually start eating again. So essentially what we're enforcing here is that you are never actually picking up only a single chopstick. You're either picking up both of them and starting to eat, or you're going to sleep, and then once your neighbor that is using one of the chopsticks you need finishes eating, they will signal you saying, now you can wake up and actually take both chopsticks and start eating again. Make sense? Questions on this? Okay, so a good question to ask here is these are two sort of contrived problems we looked at. Why do we actually care about this kind of stuff? It's sort of an amusing little problem, but why is it actually important? So this is essentially a general example of needing multiple resources in order to proceed. And this is a problem that you actually find quite a bit in practice, where you want to be able, in order to do something, you have to basically take control of multiple resources. But the problem is if you're not careful, you may end up taking some of the resources, not being able to take them all, and then end up causing a deadlock. So, this is a very simple example of that, but, this problem of basically avoiding deadlocks through through unintelligent resource allocation is actually an important one. And so next class, we're basically going to be talking a lot more about the specific problem of deadlocks, when they occur and how we can sort of avoid them in a very general way. So we just have another minute or two, but very briefly, I just want to mention, this is essentially the dining philosopher problem using semaphores, and this is basically the same idea that we already talked about. For each philosopher, while true, the philosopher is going to think, and you're going to then either pick up both forks or chopsticks or what have you, and either you'll be able to pick them both up or you'll block, then you'll eat and you'll put them down. This is essentially the same thing we already looked at. Here we're explicitly managing the locks again, but we again have this test thing which is looking at the state of the left and right chopsticks, and the logic is essentially all the same. So that's pretty much it. So remember we talked about the reader-writer problem, where we're looking at allowing multiple readers to concurrently access data. Of course, only one writer is allowed. And we looked at two different solutions. You could favor either readers or writers. Both are not really fair, but you could do either one depending on what you actually want your application to do. But you can get starvation in either case. And then we looked at dining philosophers, where we're looking at a simple example of taking multiple resources at once that you need to proceed, and doing that while avoiding a situation where everything deadlocks. So I think we'll stop there.